Hello everyone, my name is Dan and today I would like to talk to you about semantic cut elimination for the logic of bunch applications. Let me start briefly by explaining the title and the main topic of this work. The logic of bunch applications, or BI for short, is a non-classical logic used for reasoning about separation and disjointness of resources. In particular, it forms the propositional basis for separation logic, which we have seen during some of the talks yesterday. Cut elimination refers to a standard result in the proof theory of logics. We will see the precise statement later, but essentially cut elimination implies that for every formula phi, if phi is provable at all, then there exists a proof of phi which only mentions subformulas of phi. That is, only formulas that already occur in phi itself. The proofs of cut elimination for various logics that you see in the literature are usually very involved and contain a lot of details and case analysis. In this work, I propose a semantic approach to proving cut elimination for BI, by which I mean a proof that goes through some semantical model. I believe that this kind of proof is more amendable to formalization and more extensible. To support this claim, there is a co-formalization of this proof, including some extensions, available online. In the remainder of this talk, I would like to explain the problem in more detail and sketch the proof. I will conclude the talk with some reflections on the formalization process. Let's first talk about the logic of bunch applications. BI is the logic that you obtain by freely combining intuitionistic logic and multiplicative linear logic. It has the usual connectives like disjunction, conjunction, and so on, but it also includes linear connective, empty, star, and the magic wand. Intuitively, propositions in BI denote ownership of resources. For example, phi star psi holds for disjoint resources or separate resources, and the empty proposition states that there are no resources available. Like many logics, BI comes with a proof theory in a form of sequent calculus. Sequent calculus is a logical system in which one reasons about judgments of the form context, proofs, formula. So you have a formula on the right-hand side of the turnstile, and you have a context, which in the case of intuitionistic logic is a list or multiset of formulas. We think of a context as a list of hypotheses or assumptions. For each connective, there are two corresponding rules. A rule which tells you what to do if you have a connective on the left-hand side of the turnstile, and a rule which tells you what to do if you have a connective on the right-hand side of the turnstile. Here you can see the left and the right rules for the intuitionistic conjunction. The left rule says that if we have phi and psi as an assumption, then we can split it into two assumptions, phi and psi. The right rule says that if you want to prove phi and psi, then we need to have separate a proof of phi and a proof of psi. We also have structural rules. In intuitionistic logic, we have contraction and weakening. Contraction states that we can duplicate whatever assumptions that we have in the context, and the weakening states that we can throw away any assumptions that we don't need or we don't want to. In the sequent calculus for BI, the two connectives conjunction and star are externalized as two different operations on the context. Whenever we see conjunction, we connect the two resulting formulas using a semicolon, and whenever we see star, we connect the formulas using a comma. Crucially, only the semicolon admits the rules of weakening and contraction. This corresponds to the idea that conjunction behaves intuitionistically, while star behaves linearly. So, because we have two types of connectives on the contexts are no longer lists or multiset of formulas. Instead, the contexts have this tree-like shape and are called bunches. So the nodes in this tree are labeled either with a comma or a semicolon, and the leaves are formulas. Because of this nested structure of context, the left rules and the structural rules, they all can be applied deep inside a bunch on some particular substrate. Finally, the last rule of the sequent calculus to mention is the cut rule. It says that if we can prove some formula psi, then we can essentially use psi as our assumption. And intuitively, the cut rule allows us to prove and use intermediate lemmas. Alternatively, you can think of the cut rule as a rule that forces the probability relation to be transitive. An important meta-theoretical result about sequent calculus is the Cut Elimination Theorem. It states that everything that is provable is also provable without the cut rule. That is, if we have a proof of some formula phi, then we also have a proof of phi in the sequent calculus without the cut rule. And here on, we're going to use this notation, turnstile with a subscript, to denote cut-free probability. Cut elimination is important because it implies the subformula property. If there is a proof of phi implies psi, then there is a proof of it that only involves formula that are already present in phi and psi. As such, cut elimination is an important ingredient in the proof search toolbox. The usual way of proving cut elimination is syntactic or direct. It basically proceeds as following. Given a proof derivation, we look at the first instance of the cut rule that we can find, and basically we do a case analysis by looking at which derivations were used in this rule. Then we use this information to either simplify the proof or to shuffle the proof around, and in any case, what we do is we replace a particular instance of the cut rule with a number of smaller cuts for some notion of smaller. In my view, this kind of direct proofs have some limitations. Firstly, there are simply a lot of cases and details to consider. Secondly, you need to come up with the correct order in cuts. You need to define what it means for one cut to be smaller than the other, and to show that this is in fact a well-founded relation. Doing this can sometimes be tricky, especially in presence of explicit structural rules. Also, and this is specific to the case of BI, we have this tree-like shape of bunches of context, and the fact that rules can be applied deep nested inside the bunches. All of this significantly contributes to the complexity. Because of these factors, non-formalized proofs of cut elimination found in literature can be quite fragile and known to be error-prone. In fact, for some of the logics, formalized proofs of cut eliminations uncovered a number of errors or mistakes in the original pen and paper proofs. Nonetheless, formalizing this kind of proofs directly can be quite tough. The sheer number of cases and syntactic complexities makes it tedious and laborious. And complicating terminating measures and additional friction, at least in the proof assistants like Coq, which are more geared towards things like structural induction and structural recursion. Instead of formalizing a syntactic proof, I would like to argue for what I believe to a more tractable proof of cut elimination, a semantic proof. By semantic proof, I mean a proof that goes through some model C, which has a particular nice property. The property that we want is that if a formula phi holds in the model C, then phi is provable without using the cut rule. As a side note, as models, we'll consider algebraic models, so BI algebras. The details of what is a BI algebra is not important, but essentially it's a set with a preorder and all sorts of functions and operations that allow us to interpret BI connectives. What you need to know is that BI algebras are sound with regard to the sequent calculus, meaning that if phi proves psi is derivable, then the interpretation of phi is going to be below the interpretation of psi. So the way I'd like to think about it is to take inspiration from the proof of completeness. A typical algebraic completeness proof goes through what is called a Lindenbaum-Tarski algebra, which is defined in the following way. For each formula phi, we associate an equivalence class of formulas that are interprovable with phi. We then say that the equivalence class of phi is below the equivalence class of psi if phi proves psi. This turns out to be a well-defined partial order. Then the collection of all equivalence classes with this order forms a BI algebra. An important property of this algebra is that the interpretation of a formula phi is the same thing as the equivalence class of phi. Now, this model allows us to prove completeness. If phi implies psi holds in all the models, then in particular, the interpretation of phi is going to be below the interpretation of psi in this model L. This in turn means that phi proves psi, and this concludes the completeness proof. As you can see, the real work here is to show that L is indeed a model and that it has this particular property about its interpretation. So as a starting point for cut elimination, we can consider just using cut-free probability instead of regular probability in the definition of L. However, we will run into the following problem. We need to show that the ordering of the equivalence classes is intransitive in order for it to be a partial order. However, showing this is essentially showing the transitivity of the cut-free probability relation, which amounts to the same thing as showing cut elimination. So we are back to square one. In order to mitigate this, instead of using equivalence classes, we are going to consider sets of predecessors in the following sense. For each formula phi, we are going to associate the principal set of phi, which is the set of contexts from which you can prove phi without the cut rule. Then we are going to consider set inclusion, which is automatically a transitive relation. Subset inclusion is a good candidate for the following reason. First, note that every formula is included in its own principal set. That is because for any phi, phi proves itself without the cut rule. Then, if a principal set of phi is included in the principal set of psi, we can safely conclude that phi proves psi without using the cut rule. However, the collection of principal set with a subset ordering is not going to form a BI algebra. In particular, we cannot use the sets-theoretic operations such as that union and intersection of sets because principal sets are not going to be closed under those operations. We resolve this issue by forcibly closing the principal sets under arbitrary intersections. That is, the elements of the algebra that we're going to consider are going to be sets of this form, where I is an arbitrary indexing set and phi I is a formula. Now, there is actually an abstract mumbo-jumbo reason for why this works and why this forms a BI algebra, but essentially it boils down to this. So we have this closure function. It takes an arbitrary set X of bunches and returns the smallest set in C, which contains the set X. It turns out that this function allows us to transfer a lot of the operations from the power set algebra to the algebra C. For example, the disjunction in C corresponds to the closure of the union of two sets. And the star operation can also be written in terms of the closure operation and some monoidal product on the power set algebra. Finally, this model satisfies the property that we want. If the interpretation of phi is included in the interpretation of psi, then phi proves psi without the cut rule. Then, if a sequent phi proves psi is derivable, we know that the interpretation of phi is going to be included in the interpretation of psi, which will give us a cut-free proof rule of the same sequent. To sum up, this gives us a semantic-based proof of cut elimination by going through this algebra C. I believe that this approach is more modular and more amendable to formalization, at least in proof as instance like Coq. In the paper you can read more details about the proof and also about two extensions that we consider. Extensions of BI with some classes of structural rules and extensions of BI with a box modality, which is an S4-like modality added to BI. Now, before I finish, I would like to say a couple of words about the formalization. The basic formalization, without the extensions, is around 650 lines of specs and 2,500 lines of proofs. I tried a number of different representations for the elements of the algebra C, and I found the extensional representation the easiest to work with. By extensional representation, I mean that the elements of C are essentially predicates or bunches, or sets of bunches, that satisfy some particular closure property, which is a proposition. This is opposed to a more intentional representation, which would code elements of C explicitly. In order to reason with this representation, it's good to have propositional extensionality. For this, I use setoids and setoid rewriting. Setoids are actually used in lots and lots of places in the formalization, And the standard library that I use, stdpp, it has a number of type classes that integrates it very well with the whole setoid business. So overall, I have to say that I had a very positive experience with this sort of stuff. And finally, there were still places in the proof where you would have to reason about some syntactic things. For example, it is very common to have equations of this form where you can decompose a bunch delta into a sub-bunch gamma and some context delta prime. I find it useful to make inductive characterizations of such equations as inductive predicates in Coq. That is, you write down an inductive system that would generate all the equations of this form. Then you can use the normal co-induction principle to reason about these equations, which turns out to be very nice. You can see more details of this in the paper. Thank you very much for listening, and let me know if you have any questions.